Hi everyone. We will present our medical imaging term project called Realistic MRI Simulation with Non-idealities. We have used brainweb dataset for our project. We implemented MRI imaging on phantom images downloaded from brainweb dataset. Image acquisition is applied using the concepts of slice selection and k-space acquisition, in which we apply gradient echo and spin echo sequences. Then we implemented image reconstruction, where the non-idealities of MRI image are taken into account. Magnetic resonance imaging is a successful imaging technique considering the developments of soft tissue contrast and resolution. Atoms with odd number of protons and neutrons are imaged according to nuclear magnetic resonance. The concept of spatial resolution is applied with the instruments of gradient coils, RF coils, and main magnet. The simulator takes the anatomical model of brain using the brainweb dataset and has parameters adjustable for different tissue types. The output of the simulator is a realistic MRI image of the brain, in which the non-idealities of chemical shift, random noise in B0 field, T2 and T2 star decay during signal acquisition, and proton density effects are taken into account.
For our simulations, first we need to select a slice and excite only that slice of the phantom object. For this purpose, we are using a complex sinusoidal with a sinc envelope, as you can see as the B1 of T. Here you can see an example sinc envelope, and the bandwidth of the sinc envelope given by delta nu is directly related to delta z, which is the slice thickness that we are selecting. The tip angle alpha is given by this relation, and it is gamma a for a duration of a rect pulse that is centered at the nu bar, and it has a bandwidth of delta nu. Here you are seeing a blurred slice profile due to using a windowing function on the sinc envelope. In our simulations, we have not accounted for this blurred slice profile, and we have only assumed a perfect rectangular pulse. For the k-space acquisition, we are implementing both gradient and spin echo pulse sequences, and for both of them, we have implemented a rectilinear data acquisition diagram, as you can see on the screen. After these pulses, the signal that we receive is given by a Fourier transform relation, where the frequencies are given by kx and ky, and they are determined by the applied x and y gradients.
The brainweb dataset is used since it involves values related to the T1, T2 proton density and chemical shift for different tissue classes. The discrete anatomical model is used with 3D tissue volumes. For our implementation, the field of view in x direction is 181, whereas the field of view in y direction is 217.
For the implementation, we are assuming a steady state longitudinal magnetization MZ after a lot of repetition times in the pulse sequence, and it is given by this relation. Afterwards, the image that we are trying to resolve, which is f of xy, is proportional to this steady state longitudinal magnetization multiplied with the sine of the tip angle alpha. To account for chemical shifts, we are implementing a 3.35 ppm shift in the Larmor frequency for fat-only regions. Also, to simulate variations in the B0 field, we are adding random Gaussian noise on top of the 1.5 Tesla B0 field. For T2 and T2 star decay during signal acquisition window, we are multiplying the image that we are trying to resolve with a decaying exponential term. And lastly, for proton density effects, we are using this multiplier for the M0 variable. You can see the MRI parameters that we have used in our simulations, which are changing with pulse sequence type and also the contrast type. As you can see, for almost all of our simulations, we have used a tip angle alpha of 90 degrees. However, in T2 star weighted, it's set to pi over 10. And you can see the TR and TE values in milliseconds on this table.
In the simulation results part, we will first show the effect of chemical shift. On left, you see a T1 weighted gradient echo image with ideal conditions. In the middle, you see the same image with the chemical shift. The image on the right is the difference between the ideal image and the chemical shift non-ideality image. On the left image, you see the effect of random B0 variations effect on the T1 weighted gradient echo image. In the middle, you see the effect of PD non-ideality. On the right, you see T2 star decay non-ideality. And now, on the left, you see the effect of proton density non-ideality over T2 weighted image. In the middle, you see the effects of chemical shift non-ideality over T2 weighted spin echo image. And in the right, you see the effect of PD non-ideality for PD weighted spin echo image. We get better contrast for PD weighted image when we have PD non-ideality compared to without any non-idealities. On the left, you see the chemical shift non-ideality effect over PD weighted image. On the right, you see different weighted images without any non-ideality. First one is T2 star weighted image. The second one is T1 spin echo weighted image. The third one is PD weighted image. And the last one is T2 weighted image. These are our references. Now, let's pass to simulation. In the simulation, first you need to give the phantom image. Then you can pick different contrast modes and pulse sequences. Let's pick T1 weighted image with gradient echo pulse sequences. Then you can pick different non-idealities. Let's include all of them. Now we are running the code. The output is a K-space image and the output image on the figure 1 and figure 2. These are the codes for what we have explained in theory and implementation details. And thanks for listening.